This video is to talk about big O notation. So in the previous courses, we talked about the big O notation. Sometimes you will heard about big O1, that's the constant runtime, or big ON, or big ON squared. So here we will introduce what is the big O to evaluate the algorithm efficiency. So the first thing, let's talk about what is the N. So N actually here is mean in your data structure how many data you have. So that's the number of the data. So sometimes when we talk about big O1, so that's mean is the constant runtime. So this big O1 actually won't related to the size of the N. That's mean no matter your array size is 1 or your array size is 1 million. If we say this algorithm runtime is big O1 constant number, they always just runtime is 1 time. It won't affect by the size for the N. So we see the example. What is the big O1 example? So when you have the big O1 is the constant runtime, that means you have only one operation you can finish your algorithm. For example, you open a file for the input. So the open file, this action is runtime 1 because you only need to open the file 1 time. Or when you have your array, if you have an array, if you know the index, we can right away find the value. So that means big O1. That's a constant runtime. So remember, we also talk about stack and the queue implementation. So the stack queue push or pop operation is also big O1. Because remember, for example, for our stack, no matter that's the array implementation or linked list implementation, you can just find the index of the size, you will push the new value. Or in the linked list, we know where is the first node is, so we can just have the location to push the value we want to push. So that's the big O1. So a lot of time you also heard about big ON. So the big ON actually we mean is the linear timing, linear runtime. So that means if your data size is N, then to go over that runtime, you will go over the N times. The most typical one is what? Did you remember when we do the search? So this search, when we do the array, you will see when you have an array, you want to find the match value. So we have to write a for loop. So the for loop starts from I equal to 0, I less than the N. So this N actually is the size for the array. So if we find the match value, we finish. So here you will see sometimes you are lucky. The first element, the first index, you find that. So maybe you just need to do the comparison 1 time. But if we don't have this value in the array, even you finish the whole for loop, you still cannot find that element. So that's why you will see after you go over N comparison, you still cannot find that. Right, so that's why sometimes when we say the big O runtime, you may have the best case. So like here we say the best case in the example, maybe just the first couple comparison you find the match value. So that's almost runtime is 1. But also you have the worst case is you compare N times, you still cannot find that. So that's how many times you will do that, that's N. So here I just want to tell you about, when we talk about the big O runtime, we are not evaluate the best time. We are not evaluate the worst case. Actually, big O runtime, when we use the big O to do the notation, we are consider the average runtime. So that's why whenever you see a for loop, right? So even we're best, so our best case is 1, our worst case is N. So the average case is we kind of can say they are equal to n divided by 2. So when we're using the big O notation, we only care the exponent for your n here. Because half n or n doesn't matter. For example, when you have n times, right? So maybe your runtime is 1 minute or 2 minutes. We care is about the unit. So that's why the coefficient, we don't really care. So then when you have a for loop to do the searching, no matter you do the array or linked list, that's why we will say here, your big O is n, because the first thing we consider average case. The second thing, we don't care about your coefficient for the coefficient for the polynomial. The highest degree for your polynomial. So that's the big O(n). So coming back, you will see we have the constant runtime, linear runtime. So the next one you heard about a lot is n squared. So usually n squared runtime, we call that quadratic runtime. So what this one is, so one for loop, if you have one for loop, we consider the big O is n. So on the other hand, if you have 2-layer for loop, that's n squared runtime. So the typical example is we see here. Did you remember we show you the sorting? The sorting algorithm, we will talk about many. So sometimes the nested for loop sorting, like we show you in the class. Or if you talk about insertion sort, selection sort, or bubble sort from your COMSC210Module9Clip1. All those sorting, they all have 2-layer for loop. So that's why the runtime actually bring up to the big O n squared. So this one we call the quadratic runtime. So usually what is quadratic runtime? You see you have a nested for loop. So we pretty much go over everything. So we have the constant runtime, big O n, and n squared. So the next one you see, if you have the log n, so the log n actually is not a linear search. So earlier we talked about here, you have one for loop, right? This one we call the linear search. No matter that's the array or linked list, you all need to go through a for loop, go over each element from your data structure. But if I'm not sure, did you guys talk about the log n? So this log n actually we are not doing the linear search. We are doing the binary search. So when we do the binary search, you will have an array actually is in the sorted order. So that's why when we do the searching, right, we are not doing one by one. So instead here, if we have an array, so we don't need to go one by one. So here, if your array already sort, so we have from low to high value. So this binary search can help us is since we know the value will be in the order. So I don't start searching from beginning. So actually every time I just start from the middle index. So if the middle index value is greater than my target value, so we know your searching the value possibly will be this half. So then we just bring down and bring down and bring down. So this one is we call the binary search. If you didn't do that in your previous 165, so then later I will give you some other link. You can go over that. But one thing is, since we not doing the for loop for the visit all element, we do half and a half and a half. So that's why. So for two to the case power equal to the total n. So that's why we only need to do the k times comparison. So this k, you know, k will equal to the log n. So the log, actually the base is 2, it's not 10. So that's where our log n runtime came from. So that's our log n runtime. So the log n runtime is the binary search. So here, if you have the n log n example, this one we will talk about in module 13 when we talk about some advanced sorting. When we have those sorting, we like the quick sort, merge sort, or heap sort, we're using the divide and conquer sorting algorithm. So this one actually means you don't need to have a nasty for loop. Instead, I still need to go over element one by one. But the inner loop, we will have some other algorithm. We will divide that into half. So very similar like the binary search. When we divide half and half and half, they can bring down your runtime to log n. So that's the n log n runtime. So that's what we call the linear algorithm, arithmetic runtime. So those runtime you will see, actually they will have the table like this. What really that mean? So you can see when you have the big O1, I don't really care what is the data, how many data in my data structure or in my collection. So I always have one time I can find the value. Like when you do you have index, you try to find the value in the array. But when you do the nested for loop, you will see your runtime will be increment like your data size. So that's the linear increment. So the n squared will be worse. You can see because every time they do the n squared, so they will dramatic bring up our runtime. The typical example is your homework assignment 4. When we first time we do the DVC scheduling. So that's why your runtime is so long. So then afterward, actually, when we do the assignment 5, when we do the two-dimensional array, so actually we bring down our runtime kind of like n log n. So you see here, even you still have this log n, but log n compared to n, actually they are pretty close. The close mean you see here, if I have 1 million data, I run my big O, n will take 1 million operation, but n log n only becomes 6 times. So the 6 million operation. So for example, if 1 million data, I can finish in 1 second, but n log n, I only need to take 6 seconds, I can finish that. So that's briefly to talk about the difference between all different big O notation. So what's the difference for their runtime effect by the size n? And also remember one thing is, whenever we use the big O notation, we are consider the average runtime. And most of the time, we are not consider the small size n. We always consider is the big size n. So that's the big O notation.